All right, everybody. 4 o'clock. Welcome back to your favorite class. Yes. All right. Hopefully, we like the meme today. I think this is from like I don't even know, the 20-year-old Spider-Man version. I think there's been like 8 new remakes since this old Spider-Man show with Willem Dafoe. Yeah. Okay. They've had like 14 Spider-Man actors since then, so just getting a little old. But what's that? Willem Dafoe's from Milwaukee? I didn't even know that. Where's Willem Defriend from? I'm just kidding. Get it, opposite of foe. Okay. We like the haircut more. Yeah, I was so stressed out, all my hair fell out. Okay. Yeah. As you can see, I'm back in person. So if you want to come to in-person lectures, please do that Tuesday and Thursday. So it would be nice to see you back. And I got a couple people here in person, so it's nice to see you guys. A couple of announcements. Good job on the test. 82 average, so pretty good. Most people sort of had a good handle on that. I didn't have a lot of time to give you a ton of calculation type stuff just because we only had 50 minutes, and a lot of the material anyway in the class in the front end was sort of qualitative anyway. So I tried to spend a little bit more time and a few more qualitative questions. The final exam will not be that way. You will have more workout problems because we're getting into a lot more quantitative type stuff. So the final exam will have much more calculation and you have more time to do it. So there you go. Keep that in mind. Otherwise, generally good job. Homework number 5, which is on anisotropic materials, due Thursday. Questions? David says we like the haircut. That's very nice, David. Thank you. Sucking up worth 0 points. It's funny that this meme here, because actually the pen that I write with broke while I was in Pennsylvania, and I had to get like a new stylus for it. And turns out there's additional like touch styluses on the back of my writing pads. Like really, they did a really good job designing it. So good for them. So I'm somewhat of an engineer myself. I put a new stylus in there. So good job. They don't give you a PhD for nothing, I tell you. Okay. Back to where we were. Okay. I'll just run through this quickly where we sort of left off. We were talking about thin laminates. We had done this, Hooke's law in full 3-dimensional form with your 6x6 compliance and 6x6 stiffness matrices. Man, say that 6 times fast. 6x6 stiffness matrix. Okay, yeah, it's a lot. We were making a reduction from the full 3D case to a more simplistic case for thin laminates, which is a large class of composite materials. Specifically, if you're ever making like a laminated composite, they end up being quite thin. So we're going to make reductions for thin laminates. So we made a couple of assumptions here, more or less that thin laminates are going to exhibit plane stress conditions, right? So if thin, our stress conditions are going to be plane stress. So meaning that axis that comes off the thin section would be considered like the 3-axis, even though we don't, we'll call it the 3-axis. That's going to basically have 0 stress components, all right? So we're saying that the out-of-plane stress then is going to be 0. So the sigma 3 is 0, and the associated shear stresses are also 0 in that direction. So what we did is we looked at the full 6x6 compliance matrix and drew it down to a more simplistic 3x3. So here's your full 6x6 sort of Hooke's law that represents 3 dimensions. And we are drawing it down to a more simplistic case where we only have stresses that could be applied in the plane. It's like the sigma 1, sigma 2, sigma 6. Or if you want to think about it as sigma 1, sigma 2, and tau 1, 2, it might be a little bit more easy to wrap your mind around. Remember, this here is like tau 1, 2. We just abbreviate it as sigma 6 because that's what we do. And we could draw this down and simplify this quite a bit by looking at what strain equations sort of result. And it's more or less in-plane strain equations with one additional strain equation that pops out this out-of-plane stress equation here. And so the idea is we could take these in-plane strain components, which is like epsilon 1, epsilon 2, and gamma 6, and sort of rewrite this in sort of a plane stress, sort of contracted 3x3 matrix to represent a new Hooke's law for a material that's in plane stress. So this contracted Hooke's law for plane stress, we wrote this as the strain in terms of just in-plane stresses, and that reduces things from like a 6x6 condition, which is a little overbearing and a little overwhelming, to a 3x3 condition where we just have sort of this in-plane kind of components. All right. And so this is going to be hopefully getting to be more comfortable for you, because what you do in 2004 and 3005, your mechanics and materials classes, you're usually looking at elements that look like this, right? These two-dimensional elements that have like stress in one direction, stress in two direction, and shear stress on that element. We're going to like work with this sort of element almost exclusively moving forward in the class. And it, when we're talking about stresses here, this is like in-plane stresses. It's very reminiscent of things you're going to do in 2004 and 3005, not the years, the classes. And we'll start to see now what orthotropic behavior, how that influences things that you might have seen and developed in 2004 and 3005. We just had to sort of take a long way, starting with like the full 3D form of Hooke's law, to sort of get down to a position where we can sort of actually talk about this in-plane components. All right. Now, we do have this 3x3 matrix here that represents the strains in the plane. So strain in the one direction, the two direction, and the shear strain 1, 2. But there was also that out of plane strain component that resulted as well, that Mr. Turasek sort of pointed out at the end of last lecture. Remember, when you have plane stress conditions, you still have strain in the third direction. So don't forget that. That's something you should have learned in 2004 or 3005. So just because for plane stress, that just because you have sigma 3 equals 0, you will not have epsilon 3 equals 0. In fact, epsilon 3 equals this. So something that you might want to keep in mind. All right. This is a kind of an assumption of plane stress conditions. No stress in the third direction, but you will have strain in the third direction. Okay, so let's move forward and talk about these like compliance and stiffness matrix in these like plane stress conditions. All right, so let's dive in a little bit more on this, and we'll talk about this plane stress compliance matrix. Okay, so we've reduced from this full 3D this full 3D configuration to this 2D configuration. And so now we're writing Hooke's law as the following. And that is, well, let's do the full for now. Like epsilon 1, epsilon 2, and gamma 6 is equal to this compliance matrix S11, S12, 0, S12, S22, 0, 0, 0, S6, 6. Remember, because we contracted 4, 5, and 6, multiplied by the stresses in plane sigma 1, sigma 2, and sigma 6, or what you might want to think of sigma 6 as tau 1, 2, etc. So this sort of like abbreviated version, we're going to write in shorthand as the following. Epsilon plane stress, that's sort of our designation for what we're going to do moving forward. This is a plane stress condition. Is this compliance matrix S plane stress multiplied by the stress matrix in plane stress. Just a helpful designation for us to sort of put the subscript on these matrices to understand that we have plane stress conditions on these matrices, and that these now are 3 by 1, this is a 3 by 3, and this is a 3 by 1. And putting that like little plane stress symbol is going to help us sort of keep that sort of in mind. We can still write these compliance matrix entries in terms of material properties. That doesn't really change. So can still write entries of S in terms of material properties So what I mean by that is like S11 is still 1 on E1. S12 is still negative nu 1, 2 on E1. S22 is still 1 on E2. And S66 is still 1 on G12. All right. So we can still populate this compliance matrix just like in the same way that we did for the full 6x6 configuration. All right, so that's your plane stress compliance matrix in all its glory. We also might want to talk about the plane stress stiffness matrix. And this is a bit strange to me, but it's just sort of convention for composites for, I don't know, whatever reason. But when we talk about the plane stress stiffness matrix, for full 6x6 matrix, we use this like C variable. It's like C matrix, right? We know that we've seen that before. For instance, like to write that stress is equal to C times strain, right? But for some reason, we use a different variable when we're talking about plane stress stiffness matrix. This is just sort of by convention, so you don't have to write like the PL, the plane stress, subscript on the matrix every time that you talk about the stiffness matrix. So for plane stress stiffness matrix, which is 3x3, they use the variable Q for questionable reasons. Someone made a punny joke when I said that I had to fix my pen. They said pen broke Sylvania. That's pretty good, Chrissy. It's funny. Pen broke Sylvania. Where pens go to die. So in that situation, we'd have something like the stress matrix in plane stress is equal to Q times the strain matrix in plane stress. It's a little bit weird to write. But when you see like this format up here, this is a 6x1, 6x6, and this is a 6x1. When you see this form here, it's 3x1, 3x3, and 3x1. Strange. I didn't do it. Don't shoot the messenger. Okay, and it should be pretty obvious here that the compliance matrix and the stiffness matrices are still inversions. So still have the following relationship that like Q is equal to the inversion of the plane stress compliance matrix, both of these 3x3. And that the plane stress compliance matrix is equal to the inverse of Q. And we just have this fall right out of Hooke's law for plane stress behavior. All right, so if we wanted to write this out fully, which might be helpful, These are your plane stress values. And here are your plane strain. Well, strain values in plane stress. It's not plane strain. Got to be careful with vocabulary. Rawr. So this is like your full Hooke's law for plane stress conditions written with the stiffness matrix. All right. Now you may want to write the stiffness matrix entries in terms of material properties, but again, it's kind of annoying to do that, but you can do it. It's easier than the full 6x6 stiffness matrix. So for Q in terms of engineering constants, you have the following. You ready? This is exciting. Q11 denominator is much bigger. 1 minus nu 1, 2 squared times E2 on E1. And the numerator here is E1. Q22 looks similar denominator. Oh, sorry. This is 2 on 1. And the numerator here is E2. Q12 here is nu 1, 2 E1 over the same denominator. And finally, this one's easy. Oh, that one was nice. This is G. It's a shear modulus 1, 2. All right. How we doing? We all sort of with me still? All right, I'm getting a thumbs up from the people in the audience. Anybody awake out there? Virtual land? Okay. Wake up. All right. Everything so far that we've talked about for this plane stress conditions has been the assumption that we're sort of working in principal material coordinates and we have orthotropic material. This plane stress assumption. We've been in principal material coordinates. And orthotropic. Okay, what do I mean by that? Well, that means that we're looking at sort of pictorially, that means that we've sort of been sticking with the following. If this is our laminate or our composite that has like fibers running in this direction, and we've sort of been doing everything in this coordinate system, right? Ooh, do I have a comment? I'd give you thumbs up, but my arms are still broken. Is that from writing too much? Is that a complaint, Alex? Too much writing. Don't you guys play video games? Like, come on, aren't your hands like super strong from all these video games? Okay. Play more League of Legends. Okay. But remember that we can transform our stiffness and compliance matrices using stress transformation equations, right? And so we've sort of done this so far. And so let's talk about transformations to off axes using the transformations we've already sort of established. Okay. So if I wanted to move from like these 1, 2 coordinate system into some alternative coordinate system, I don't know, say XY coordinate system. And we've sort of seen this before in 3 dimensions, but now we're just doing it in 2 dimensions. Now, your T matrix is no longer 6 by 6, but 3 by 3. And we can have a stress transformation, which looks like the following. Here I'll say this transformation matrix T, and let's use the plane stress subscript again. Multiplied by whatever you have in your alternate coordinate system. So going from XY to 1, 2, 3. Where your plane stress transformation matrix is the following. We've simplified it now quite a bit. It's a 3 by 3. Here this is m squared minus n squared. Where obviously m is cosine theta, n is sine theta. If you're going from 1, 2 coordinate system to XY coordinate system, which I'll draw like this. Usually you're going from XY to 1, 2. Here's your angle of theta. It's your rotation angle between the XY coordinate system, which you might be in, and the 1, 2 coordinate system, which you might want to go to. Right. We can do a similar sort of thing for the strain transformations. All I play is online chess trying to beat Professor Hart. In your dreams. Do you have a rating, Alex? We should play. Anybody play chess in here? No? Well, I played with Jack a couple times. He's rated 1 million. Divided by 1 million. Yeah, if you don't know the ELO system, forget it. Come by my office if you want to play chess sometime. We'll play. All right, strain transformations. Similar idea. If I want to write the strains in the 1-2 coordinate system, I would have the following. Nope, sorry, not signals. Right, where this is like your T star matrix. Plane stress. Again, same idea for M and N. Here's my value of theta. M is cosine theta, N is sine theta. All right. We're moving, we're shaking. I promise we're going to use this stuff in a little bit. Been very mathy, I know. You may not want to just transform stress and strain. You may also want to transform your stiffness and compliance matrices. So you can also do that. And that's going to, again, sort of be pretty straightforward. Or if you have like some stress X, some stress Y, some shear XY. And this is going to be equal to what would be like the stiffness matrix Q in the XY coordinate system multiplied by epsilon X, epsilon Y, and gamma XY. This is just like your general Hooke's law for in-plane stress we sort of like talked about before. But we know we can write this in terms of like Q1, 2 with transformations. Because usually we'll know Q1, 2 from like material properties, right? We could calculate what the stiffness matrix is usually for a material. And we can transform it to the XY coordinate system, sort of with the following idea. remember that we have our transformation for plane stress multiplied by what you might have, sorry, it's 1, 1. What you might have already calculated for your material from, let's say, material properties that you have. Multiplied here by T star inverse for plane stress. Multiplied by your applied strains in the XY coordinate system. Okay. So here, this guy would be like your Q in the XY coordinate system. This stiffness matrix that is not in principal coordinates, so one that is in like an XY coordinate system, we typically label as Q bar. Also the compliance matrix as well. So those not in principal coordinates are given as S bar and Q bar. It's a little bit strange, but it helps us keep track of, like, am I in principal coordinates with the stiffness matrix or not? So this QXY here is actually typically written as Q bar. So that bar over the top just tells you that you're not in your principal coordinates. Then in shorthand, you'll typically see Hooke's law for plane stress is something like sigma xy, this is a 3/1, is equal to Q bar times epsilon xy, where Q bar is T of plane stress times Q times T star inverse for plane stress. Nope, sorry, that's the wrong way. You can see a lot of MATLAB coming in your future. You can feel it. I know it. Xavier already has a headache. All right, also, your compliance matrix. In the XY coordinate system is this S bar times the stresses in XY. We hear S bar T star inverse for plane stress multiplied by your principal coordinate stiffness matrix S multiplied by T for plane stress. Yikes. Okay. Now remember that like these guys here are transformation matrix that basically contain like cosine theta, sine theta, and all these sorts of transformation variables. Same thing with this guy here and this guy here. So if you wanted, you could sort of symbolically multiply the principal stiffness and principal compliance matrices out against these transformation matrices. Okay, so remember that these guys just contain, they're just like full of like sines and cosines. Okay, these are 3 by 3, full of like sine theta and cosine theta, right? So can write this S bar in terms of your original compliance matrix and sine theta and cosine theta terms. If you like multiply all of this out symbolically. Similar for, sorry, Q. I'm about to show you something. Don't write these down. Your hand will really fall off, okay? If you did that, I'll give you a second to copy what I've written. If you did that, you would end up with this, okay? Here are each of the individual entries of the rotated stiffness and compliance matrices in terms of the original values of the stiffness and compliance matrices. So for instance, these guys here, Q11, Q12, Q66, you can write them in terms of material properties that you already know. We wrote what those values would be down a couple of slides ago. Right? You could also do the same thing for S11, S12, S66, right? So S11 is just 1 on E1. S12 is negative nu 1, 2 on E1. S66 is 1 on G12. S22 is 1 on E2, right? And if you're trying to get what is like the S bar 1, 1 entry in some new coordinate system, just figure out what the rotation angle is between the coordinate system that you have and the coordinate system that you originally had. That value of theta should be easily understood, and you can just plug and chug into all these equations here to figure out what are the compliance matrix entries in my off-axis coordinate system. Complicated, dang, but really it's not. All right. So that's just sort of this equation and this equation just fully multiplied out. Man, a lot of stuff going on there. All right. Okay, last thing I want to talk about today is sort of engineering constants in those off axes. So we talked about engineering constants in like the 1 direction, the 2 direction, the 6 direction, blah, 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 blah. Okay, so we have engineering constants in principal directions. That's like 1, E2, nu12, G12. How do we usually get those? Someone, tell me. You just did it on your test. How do I determine E1, E2, nu12, and G12 if I have material properties of the constituent that makes up my composite? Yeah, micromechanical models. Right? You just did this on your test. Okay. These can feed into like S, right? So you get your compliance matrix that way. Right? Then you can like invert to get Q. Okay. Where these are just like your principal material coordinates. Yes? Okay. But now what if I want the modulus in some arbitrary direction? Let's say EX, EY, new XY, or GXY. How do I do that? So the picture you want to have in your head is I've got some thin laminate. Here are the fibers that are running inside my laminate. Okay. So I've got like the 1-2 direction, which I generally know. But I want to rotate, or I want to determine, let's say I have some other coordinate system here, like the X direction and the Y direction. You say like, what is EX, for instance? The stiffness of this particular laminate in some arbitrary orientation. We're going to apply the same idea here that we applied in the past to figure out how we write like S in terms of E1, new 1, 2, and E2. We're going to do the same idea here. Is we're going to figure out how we can write, you know, S in terms of EX, EY, GXY, etc. And what we're going to do is we're going to run mock tensile experiments in the X direction. So we'll apply sigma X and investigate response. Geez, spelling is hard. So remember we kind of did this before. Where we had like, all right, what is strain in X, strain in Y, gamma XY? If we have our sort of compliance matrix, which is S bar 1, 1, S bar 1, 2, S bar 1, 6, S bar 1, 2, S bar 2, 2, S bar 2, 6. Remember, this is the compliance matrix like in the XY coordinate system. Multiplied here now just by sigma X. The result is that epsilon X is equal to S bar 1, 1 times sigma X. epsilon 1, or epsilon y is S bar 1, 2 times sigma x. And gamma xy is S bar 1, 6 times sigma x. Those are the equations that sort of result when we do this mock experiment. But if we're looking originally for a modulus in the x direction, remember what that actually means. We know the modulus in x is simply going to be the stress in the x divided by the strain in the x. Or here, that's stress in the x divided by S bar 1, 1 times sigma x. And it comes right from here. Cancel this guy, cancel this guy. And you see that the modulus in the x direction is just 1 over the 1, 1 entry of this transformed compliance matrix. This looks very similar to like that guy. Okay, that's where we'll stop today. We'll talk about other engineering constants when we pick it up. And that's it. Alex, you have a rating of at least 2,000? No. My rating's about 1,300. I think last I checked, I was 1277 USCF. $2,000, man. You gotta be like a grandmaster to be 2,000. God. Yeah, it's Alex.